Today's video is based on Chapter 1 Class 9 Matter in Our Surroundings. Before starting this video, please subscribe to my channel linked in Pharma. Introduction on Matter in Our Surroundings. Exploring the substances around us. Matter, the fundamental substance that makes up everything in the universe, exists in various forms around us. This brief exploration delves into the properties and states of matter, shedding light on its diverse manifestations and interactions within our immediate environment. Physical nature of matter. The physical nature of matter encompasses its fundamental attributes and behaviors that define its existence and interactions. Matter is composed of tiny particles called atoms and molecules, which are in a constant state of motion. These particles exhibit properties such as mass, volume, density, and temperature, which help classify and differentiate various substances. Matter exists in three primary states: solid, liquid, and gas, each with distinct characteristics. Solids have a fixed shape and volume due to strong intermolecular forces that hold particles closely together. Liquids lack a fixed shape but maintain a definite volume, with weaker intermolecular forces allowing particles to move more freely. Gases, on the other hand, possess neither a fixed shape nor volume, as particles have high kinetic energy and move independently. The physical nature of matter also involves changes in state, such as melting, freezing, vaporization, and condensation, which result from alterations in temperature and pressure. These changes reflect the energy transfer between particles, affecting their arrangement and motion. Understanding the physical nature of matter is crucial in comprehending everyday phenomena, chemical reactions, and the properties of materials in the universe, enabling us to harness and manipulate substances for various purposes. Matter is made up of particles. Matter is composed of tiny particles known as atoms and molecules. These particles come together to form various substances with distinct properties and behaviors. Here are some examples of matter and the particles they are made up of. 1. Water. Water is a compound made up of molecules. Each water molecule consists of two hydrogen atoms bonded to one oxygen atom. Water exists in all three states of matter: solid, ice, liquid, liquid water, and gas, water vapor. 2. Oxygen. Oxygen is a diatomic molecule made up of two oxygen atoms bonded together. It is a gas that is essential for respiration and combustion. 3. Iron. Iron is an element composed of atoms. The atoms of iron are arranged in a regular pattern in its solid state, giving it its characteristic properties such as hardness and strength. 4. Carbon dioxide. Carbon dioxide is a molecule made up of one carbon atom bonded to two oxygen atoms. It is a gas that is produced during combustion and respiration and is also a significant component of Earth's atmosphere. 5. Diamond. Diamond is a form of carbon where carbon atoms are arranged in a crystal lattice structure. It is a naturally occurring substance known for its extreme hardness and brilliance. 6. Helium. Helium is a noble gas composed of individual helium atoms. It is known for its low density and is commonly used in balloons and as a coolant in various applications. 7. Salt. Sodium chloride. Salt is a compound made up of sodium and chlorine ion. The positively charged sodium ions and negatively charged chloride ions are held together by electrostatic forces. 8. Hydrogen. Hydrogen is a diatomic molecule consisting of two hydrogen atoms bonded together. It is the lightest and most abundant element in the universe. These examples illustrate how different combinations of atoms and molecules give rise to the wide variety of substances and materials that make up our world. Activity: making a DIY Play-Doh model. Materials needed: flour, salt, water, food coloring optional, mixing bowl, measuring cups and spoons, plastic wrap or airtight container for storage. Instructions: mixing ingredients: measure and mix 1 cup of flour and 1/2 cup of salt in the mixing bowl. If desired, add a few drops of food coloring to the mixture. Adding water: slowly add 1/4 cup of water to the dry mixture while stirring continuously. Kneading the dough: once the mixture comes together, knead it with your hands until you form a smooth, pliable dough. Observations. Observe the texture and consistency of the Play-Doh. Exploration. Pull apart a small piece of the Play-Doh to reveal its inner texture. Conclusion. Discuss how the Play-Doh is made up of small particles, flour, salt, water, that have combined to form a new substance with specific properties. Storage. Store the Play-Doh in an airtight container or wrap it in plastic wrap to keep it from drying out. Explanation. This activity allows participants to create Play-Doh from simple ingredients, emphasizing that matter is composed of smaller particles that can be mixed together to create new substances. By kneading and exploring the Play-Doh, participants can physically experience how particles combine to form a cohesive material with specific characteristics. How small are these particles of matter? The particles of matter, such as atoms and molecules, are incredibly small on a microscopic scale. Their sizes are typically measured in units like nanometers or angstroms, which are fractions of a meter. Here are some approximate sizes to give you an idea of how small these particles are. 1. Atoms. Atoms are the fundamental building blocks of matter. Their sizes vary depending on the element, but they typically have diameters on the order of angstroms. For example, a hydrogen atom has an approximate diameter of about 0.1 angstroms, while a carbon atom has a diameter of about 0.2 angstroms. 2. Molecules. Molecules are combinations of atoms bonded together. Their sizes can vary significantly based on the number and arrangement of atoms. Small molecules like oxygen have sizes around a few angstroms, while larger molecules like proteins can have sizes ranging from nanometers to micrometers. 3. Nanometers. 1 nanometer is equal to 1 billionth of a meter, 1 manometer equals 10 to 9 meter. Nanometers are often used to describe the sizes of nanoparticles, viruses, and molecules. For comparison, the diameter of a DNA molecule is about 2 manometer. 4. Viruses. Viruses are much larger than individual atoms or molecules but are still quite small on a human scale. Their sizes typically range from about 20 to 400 manometer. 5. Cells. Cells are the basic units of life, and their sizes can vary widely among different organisms and cell types. A typical human cell might have a size on the order of micrometers, which is larger than nanoparticles but still much smaller than what the human eye can see without a microscope. To put things into perspective, if you were to magnify an atom to the size of a marble, then a marble blown up to the same scale would be about the size of the Earth. This illustrates just how minuscule these particles are in comparison to the objects we encounter in our daily lives. Activity: Pepper and water experiment. Materials needed: bowl or plate, water, ground black pepper, dish soap. Instructions: 1. Setup: fill the bowl or plate with water, about halfway full. Sprinkle a small amount of ground black pepper evenly across the surface of the water. 2. Observations. Observe the black pepper particles floating on the water's surface. 3. Add dish soap. Dip your finger in dish soap so that there's a bit of soap on your fingertip. Gently touch the water's surface in the center of the bowl with the soapy fingertip. 4. Observations. Watch as the black pepper particles move away from the spot where you touched the water. 5. Explanation. The movement of the pepper particles occurs due to the disruption of surface tension caused by the dish soap. This activity provides a visual representation of how tiny particles, like the pepper, are moved by the invisible forces at play in the liquid. 6. Further exploration. You can try adding a drop of food coloring or a drop of milk to the water to observe how these liquids mix and interact differently. Explanation. This activity allows participants to see how small particles like black pepper can move and spread out in response to changes in the properties of the surrounding liquid. It highlights the idea that particles of matter are incredibly small and can be influenced by even minute interactions at the molecular level. Characteristics of particles of matter. The particles of matter, such as atoms and molecules, possess several key characteristics that define their behavior and interactions. These characteristics play a fundamental role in understanding the physical properties of different substances and how they interact with each other. Here are some important characteristics of particles of matter. 1. Mass. Mass is the amount of matter in an object and is a measure of the total number of atoms or molecules it contains. Mass is typically measured in units like grams or kilograms. 2. Volume. Volume is the amount of space occupied by a substance. In the gas state, particles are spread out and don't have a fixed volume. In the solid and liquid states, particles are closely packed, and the substance has a defined volume. 3. Density. Density is the mass of a substance per unit volume. It indicates how tightly packed the particles are within a given space. Denser substances have more mass packed into a smaller volume. 4. State of matter. The state of matter refers to whether a substance is a solid, liquid, or gas. This characteristic is determined by the arrangement and movement of particles. In solids, particles are tightly packed and vibrate in fixed positions. In liquids, particles are close but can move past each other. In gases, particles are widely spaced and move freely. 5. Kinetic energy. Particles are in constant motion due to their kinetic energy. The amount of kinetic energy they possess depends on their temperature. Higher temperatures result in greater kinetic energy and faster particle movement. 6. Intermolecular forces. These forces are interactions between particles that determine how closely they are held together. Strong intermolecular forces lead to solids with fixed shapes, while weaker forces result in liquids and gases with more mobile particles. 7. Electrical charge. Particles can carry electrical charges. Atoms can be neutral, positively charged ion, or negatively charged ion. These charges play a role in chemical reactions and interactions between particles. 8. Size. Particles vary in size depending on the type of particle and the substance they compose. The size of particles affects how they pack together and their overall properties. 9. Chemical composition. The type and arrangement of atoms or molecules in a substance determine its chemical composition. Different substances have different arrangements of particles, leading to unique chemical properties. 10. Brownian motion. Particles in liquids and gases exhibit random, zigzag movement known as Brownian motion. This motion is a result of constant collisions with other particles and is a key indicator of the presence of particles. 11. Entropy. Entropy is a measure of the randomness or disorder in a system. The behavior of particles contributes to the overall entropy of a substance and influences phase transitions. Understanding these characteristics helps scientists and researchers predict how different substances will behave under various conditions and how they will interact with each other, enabling us to explain and manipulate the physical and chemical properties of matter. Particles of matter have space between them. Yes, particles of matter do have space between them, regardless of the state of matter, solid, liquid, or gas they are in. The amount of space between particles varies depending on the state and the nature of the substance. 1. Solid state. In a solid, particles are closely packed and have the least amount of space between them. However, there is still some space between particles, allowing them to vibrate in their fixed positions. This vibration gives solids their rigidity. 2. Liquid state. In a liquid, particles are still relatively close to each other, but they have more freedom to move around compared to solids. This results in liquids being able to flow and take the shape of their container. The particles in a liquid slide past one another, maintaining a moderate amount of space. 3. Gas state. In a gas, particles are widely spaced and have the most amount of space between them. Gas particles move freely and independently, colliding with each other and the walls of their container. The kinetic energy of gas particles overcomes any attractive forces between them, allowing them to spread out. It's important to note that the concept of empty space, in the context of particles of matter, is somewhat relative. Even in the solid state, where particles appear to be tightly packed, the subatomic structure of atoms and molecules themselves contains significant amounts of empty space between the nucleus and the orbiting electrons. This is due to the extremely small size of subatomic particles relative to the overall size of an atom. In summary, while particles of matter do have space between them, the amount of space varies depending on the state of matter and the specific properties of the substance. Activity: expanding balloon in a bottle. Materials needed: plastic bottle with a narrow neck. Balloon. Water. Hot water, heated on a stove or microwave. Tongs or oven mitts for handling hot objects. Instructions. 1. Preparation. Fill the plastic bottle with a little cold water, about 1/4 full. Inflate the balloon a little, but don't tie it yet. 2. Setup. Stretch the open end of the balloon over the neck of the bottle. Make sure it forms a tight seal. 3. Observations. Observe the initial state of the balloon inside the bottle. 4. Expansion. Carefully hold the neck of the bottle with tongs or oven mitts. Pour hot water into the bottle, ensuring it doesn't come into direct contact with the balloon. 5. Observations. Watch as the balloon inside the bottle expands. 6. Explanation. As the hot water heats the air inside the bottle, the air molecules gain energy and move more vigorously, causing the pressure inside the bottle to increase. The pressure increase pushes against the balloon, causing it to expand. 7. Cool down. Allow the bottle and balloon to cool down. 8. Observations. Observe the balloon after it has cooled down. 9. Conclusion. Notice that as the air inside the bottle cools down, the balloon returns to its original state. Explanation. This activity demonstrates the concept that gases have space between their particles. The air inside the bottle expands when heated, pushing the balloon out. As it cools, the air molecules lose energy, and the balloon returns to its original size. This showcases how temperature affects the movement and spacing of gas particles. Particles of matter continuously moving. Yes, particles of matter are in a constant state of motion. This movement is a result of the kinetic energy they possess due to their temperature. The concept that particles of matter are continuously moving is a fundamental principle in physics known as the kinetic theory of matter. Here are some key points about the continuous movement of particles. 1. Random motion. The movement of particles is random and chaotic. They move in all directions with varying speeds, colliding with each other and the walls of their container. 2. Kinetic energy. Particles possess kinetic energy, which is the energy of motion. As the temperature of a substance increases, its particles gain more kinetic energy and move faster. 3. State of matter. The state of matter determines the nature of particle movement. In solids, particles vibrate in fixed positions. In liquids, particles move more freely but still maintain close proximity. In gases, particles move rapidly and independently. 4. Brownian motion. The erratic movement of particles in liquids and gases, known as Brownian motion, is a direct result of their continuous random motion. This phenomenon was first observed by botanist Robert Brown and is caused by the collisions of particles with other particles and the surrounding medium. 5. Pressure and temperature. The pressure exerted by gases is a result of the constant collisions of gas particles with the walls of their container. As temperature increases, particle movement becomes more vigorous, resulting in higher pressure. 6. Diffusion. The process of diffusion, where particles spread out from areas of high concentration to areas of low concentration, is driven by the continuous motion of particles. This is evident when you smell a fragrance from a distance or when two gases mix together. 7. Melting and boiling. When a solid melt or a liquid boil, the increased temperature provides particles with enough kinetic energy to break free from their fixed positions or overcome intermolecular forces. The concept of continuous particle movement is crucial for understanding various physical phenomena, such as heat transfer, phase changes, and chemical reactions. It also underlies the behavior of matter in our daily lives and contributes to the dynamic nature of the universe. Activity: Brownian motion observation. Materials needed: microscope, optional but enhances observation. Microscope slide. Water. Small particles, examples, pollen, dust, small bits of paper. Light source, examples, flashlight or lamp. Instructions. 1. Preparation. Place a drop of water on the microscope slide. Add a small amount of the chosen particles, pollen, dust, paper, to the water droplet. Cover the slide with a cover slip, gently pressing to spread the water and particles. 2. Observations. Place the slide on a flat surface. Shine a light source from below the slide to illuminate the particles. Observe the slide using a microscope, if available, or with your naked eye. Focus on a single particle and observe its movement over time. 3. Brownian motion. Notice how the particles move in random, zigzag patterns. They appear to be jiggling and moving in all directions. 4. Explanation. This motion is called Brownian motion and is caused by the continuous collisions between particles of the fluid, water, and the smaller particles. The erratic movement of the smaller particles is a direct result of the constant and random motion of water molecules. 5. Variations. Try using different particles or liquids and compare their Brownian motion behavior. Experiment with varying the temperature of the water to observe its effect on particle movement. Explanation. This activity visually demonstrates the concept of Brownian motion, where small particles are in a constant state of random motion due to the collisions with surrounding particles. It provides a tangible way to observe how particles of matter are continuously moving, even when they are not directly observable with the naked eye. Particles of matter attract each other. Yes, particles of matter do indeed attract each other, and these attractive forces play a significant role in determining the physical properties and behavior of substances. The strength and nature of these forces depend on the type of particles and the conditions they are in. There are several types of intermolecular forces that contribute to the attraction between particles. 1. Van der Waals forces. These are relatively weak forces that arise due to temporary fluctuations in electron distribution around atoms or molecules. Van der Waals forces include dispersion forces, London dispersion forces, and dipole-dipole interactions. 2. Dipole-dipole interactions. These occur between molecules that have permanent dipoles, uneven distribution of charge, due to differences in electronegativity. The positive end of one molecule attracts the negative end of another, creating an attraction. 3. Hydrogen bonding. A special type of dipole-dipole interaction. Hydrogen bonding occurs when hydrogen is bonded to a highly electronegative atom, usually nitrogen, oxygen, or fluorine, and interacts with another electronegative atom in a different molecule. 4. Ion dipole interactions. These interactions occur between ions, charged particles, and polar molecules. The positive or negative charge of an ion attracts the opposite charge of a polar molecule. 5. Ionic bonds. In ionic compounds, such as salts, positively charged ions, cation, are attracted to negatively charged ions, anion, through electrostatic forces. This attraction creates a strong bond. 6. Covalent bonds. In covalent compounds, atoms share electrons, leading to a strong attraction between the atoms within a molecule. These intermolecular forces and attractions are responsible for various properties of matter, including boiling and melting points. Substances with stronger intermolecular forces typically have higher boiling and melting points, as it takes more energy to overcome these forces and transition between states. Solubility. Intermolecular forces influence how well substances dissolve in each other. Polar substances tend to dissolve in polar solvents, and nonpolar substances dissolve in nonpolar solvents due to similar intermolecular forces. Viscosity. The thickness or resistance to flow of a substance is influenced by its intermolecular forces. Substances with stronger intermolecular forces tend to have higher viscosity. Surface tension. The cohesive forces at the surface of a liquid create surface tension. Stronger intermolecular forces result in higher surface tension. Physical properties. Intermolecular forces affect properties like hardness, elasticity, and brittleness in solids. These attractive forces are crucial for understanding the behavior of matter in various situations. From the structure of materials to the behavior of gases, liquids, and solids. Activity. Static attraction with balloons. Materials needed. 2 balloons, different colors. Wool or a dry cloth. Instructions. 1. Preparation. Inflate both balloons and tie them securely. Rub one of the balloons against a wool cloth or your hair for about 20 seconds. This transfers electrons from the cloth to the balloon, creating a static charge. 2. Observations. Hold the two balloons near each other without touching. Observe what happens when you slowly bring the balloons closer to each other. 3. Interaction. Notice how the balloons are attracted to each other and might even stick together. 4. Explanation. The rubbing process transfers electrons, resulting in one balloon becoming negatively charged and the other positively charged. Oppositely charged objects attract each other due to the electrostatic force, which is a result of the particles, electrons, within the objects interacting. 5. Additional exploration. Try using different materials to rub the balloons and observe how it affects the attraction. Experiment with different distances between the balloons and see how the strength of the attraction changes. Explanation. In this activity, the balloons become charged through friction, and their opposite charges result in an attractive force between them. This activity illustrates the concept of particles of matter, electrons, attracting each other due to their electric charges. It's a simple and engaging way to introduce the concept of electrical interactions between particles. States of matter. The state of matter refers to the physical form in which a substance exists, such as solid, liquid, gas, or plasma. It describes the arrangement, behavior, and properties of particles within a substance based on factors like temperature and pressure. The states of matter, solid, liquid, and gas, represent different arrangements and behaviors of particles. These states are determined by factors like temperature and pressure. Solid state. In the solid state, particles are tightly packed in an ordered arrangement. They vibrate around fixed positions due to their relatively low kinetic energy. This leads to the characteristic rigidity and definite shape of solids. Examples. Ice. Water in its solid state forms a hexagonal lattice structure where water molecules are held in a fixed pattern. Diamond. Carbon atoms in a diamond are arranged in a three-dimensional crystal lattice, making it one of the hardest substances. Iron. In metallic solids like iron, atoms are arranged in a repeating pattern, which gives metals their strength and electrical conductivity. Solid state activity. Making ice cream. Activity. Making homemade ice cream is a fun way to observe the solid state of matter. You'll be freezing a liquid mixture to form a solid dessert. Procedure. Mix milk, sugar, and flavoring, like vanilla extract, in a bowl to create a liquid mixture. Pour the mixture into a resealable plastic bag. Fill a larger plastic bag with ice cubes and salt, acts as a freezing agent. Place the smaller bag with the liquid mixture inside the larger bag with ice and salt. Seal both bags tightly and shake vigorously for about 10 to 15 minutes. The liquid mixture will gradually freeze due to the cold ice and salt mixture, turning into a solid, homemade ice cream. 2. Liquid state. In the liquid state, particles have more kinetic energy than in solids. They are still close together but have enough energy to move past one another. Liquids take the shape of their container but maintain a constant volume. Examples. Water. In the liquid state, water molecules are more mobile, allowing them to flow and take the shape of the container they are in. Mercury. A unique liquid metal, mercury maintains its liquid state at room temperature due to weak intermolecular forces. Liquid state activity. Investigating surface tension. Activity. Exploring the concept of surface tension in liquids using simple materials. Procedure. Fill a small bowl with water until it's nearly full. Gently place a paperclip or small piece of paper on the water surface. Observe how it floats. Using a toothpick, carefully touch the water surface near the floating object. Notice how the object reacts. Now, place a drop of dish soap onto the water surface away from the floating object. Observe how the floating object moves towards the dish soap due to the reduction of surface tension caused by the soap molecules. 3. Gas state. In the gas state, particles have high kinetic energy and are widely spaced. They move freely and independently, colliding with each other and the container walls. Gases take both the shape and volume of their container. Examples. Air. The mixture of gases that makes up Earth's atmosphere is in the gas state. It consists primarily of nitrogen, oxygen, carbon dioxide, and other trace gases. Helium. Helium is a very light gas and is often used to fill balloons due to its buoyant properties. Oxygen gas. Oxygen is essential for respiration and is often stored in gas cylinders in its gaseous state. Gas state activity. Inflating a balloon with gas. Activity. This activity involves using a gas to inflate a balloon and observe the properties of gases. Procedure. Obtain a balloon in an empty plastic bottle. Pour a small amount of vinegar into the bottle. In a separate container, mix baking soda and water to create a gas, carbon dioxide, when combined with vinegar. Quickly place the balloon over the mouth of the bottle without letting the baking soda and vinegar mixture spill. Lift the balloon, allowing the baking soda and vinegar to mix inside the bottle. As the gas is produced, it inflates the balloon. You've trapped a gas inside the balloon. These activities can help illustrate the different states of matter and the unique properties associated with each state. They also provide a hands-on way to explore scientific concepts related to solids, liquids, and gases. It's important to note that matter can also exist in additional states under specific conditions. 4. Plasma state. Plasma is a high-energy state of matter where atoms lose their electrons, resulting in a mixture of positively charged ions and free electrons. Plasma is common in stars and lightning bolts. 5. Bose-Einstein condensate. This is a state of matter that occurs at extremely low temperatures near absolute zero. Particles lose their individual identities and behave as a single quantum entity. This state was first predicted by Satyendra Nath Bose and Albert Einstein. Understanding the different states of matter and their characteristics helps explain various natural phenomena and enables scientists to engineer materials for specific applications. Can matter change its state? Yes, matter can indeed change its state. The process of changing from one state of matter, solid, liquid, or gas, to another is known as a phase change or a state change. These changes occur when substances experience changes in temperature or pressure. There are several types of phase changes. 1. Melting, solid to liquid. When a solid is heated, it gains energy, and its particles start vibrating more vigorously. If the temperature reaches the substance's melting point, it transitions to the liquid state. The energy added breaks the intermolecular forces holding the particles in a fixed structure. 2. Freezing, liquid to solid, the opposite of melting. Freezing occurs when a liquid loses energy, usually through cooling, and its particles slow down. When the temperature drops below the substance's freezing point, particles come together in a more ordered arrangement, forming a solid. 3. Evaporation, liquid to gas. Evaporation occurs when a liquid gains enough energy from its surroundings, usually due to an increase in temperature, causing some of its particles to escape and become a gas. This process happens at the liquid's surface. 4. Condensation, gas to liquid. Condensation is the reverse of evaporation. Gas particles lose energy, often by cooling, causing them to slow down and come closer together. This results in the formation of liquid droplets. 5. Sublimation, solid to gas. Sublimation happens when a solid directly changes into a gas without becoming a liquid first. This occurs when the substance's vapor pressure at a certain temperature exceeds the atmospheric pressure. 6. Deposition, gas to solid. Deposition is the reverse of sublimation. Gas particles lose energy rapidly, usually through cooling, and transition directly into a solid without becoming a liquid. These phase changes are important in various natural and industrial processes. For example, the water cycle involves repeated evaporation and condensation, while the process of boiling water for cooking involves a change from liquid to gas. The ability of matter to change its state allows for a diverse range of phenomena and practical applications in everyday life. Effect of change of temperature. The change of temperature has a profound effect on the behavior and properties of matter, particularly on its state and its physical characteristics. Here's how changes in temperature can impact matter. 1. Change of state. Changing the temperature can cause matter to undergo phase changes. Melting and freezing. An increase in temperature can melt a solid into a liquid, while a decrease can freeze a liquid into a solid. The energy gained or lost affects the motion of particles and the strength of intermolecular forces. Evaporation and condensation. Raising the temperature speeds up the evaporation of a liquid into a gas. Cooling the gas causes condensation, forming liquid droplets. Sublimation and deposition. Increasing temperature can lead to sublimation, where a solid transitions directly into a gas. Lowering the temperature leads to deposition, where a gas transitions directly into a solid. 2. Thermal expansion and contraction. Matter generally expands when heated and contracts when cooled due to changes in the motion of particles. This phenomenon is used in various applications, such as designing materials that can withstand temperature changes. 3. Kinetic energy. Temperature is a measure of the average kinetic energy of particles. As temperature increases, the kinetic energy of particles also increases, resulting in faster movement and more vigorous collisions. 4. Pressure. In gases, an increase in temperature can lead to an increase in pressure if the volume is kept constant. This is because the higher kinetic energy of gas particles leads to more frequent and energetic collisions with the container walls. 5. Chemical reactions. Temperature affects the rate of chemical reactions. Higher temperatures generally increase the rate of reaction, as particles move faster, collide more frequently, and have greater energy for successful collisions. 6. Electrical conductivity. In metals, increasing temperature can lead to an increase in electrical resistance due to increased particle vibration, which hinders the flow of electrons. 7. Material properties. Changes in temperature can affect the material properties of matter. For example, some materials become more brittle or ductile at certain temperatures. 8. Thermal comfort. Human perception of comfort is greatly influenced by temperature. Too hot or too cold environments can affect our well-being and productivity. Understanding the effects of temperature on matter is crucial for various fields such as physics, chemistry, engineering, and even day-to-day activities. It allows us to predict and control the behavior of substances and design materials and processes that suit specific conditions. Activity. Color-changing thermochromic slime. Materials needed. Thermochromic pigment, available online or at craft stores. Clear school glue. Liquid starch or borax solution, for making slime. Mixing bowl and spoon. Hot water. Cold water. Food coloring, optional. Measuring cups and spoons. Instructions. 1. Prepare the borax solution, if using borax. Mix 1 teaspoon of borax with 1 cup of hot water until the borax dissolves. Let it cool. 2. Make clear slime. In a mixing bowl, pour about 1/2 cup of clear school glue. Add a few drops of food coloring if desired. Choose a color that contrasts with the thermochromic pigment. Slowly add the liquid starch or borax solution while stirring continuously until the mixture starts to form slime. You might not need all of the solution, so add it gradually. 3. Add thermochromic pigment. Sprinkle a small amount of thermochromic pigment, usually just a pinch, onto the surface of the slime. Gently knead the slime until the pigment is evenly distributed. 4. Observe color change. Play with the slime and observe its color at room temperature. 5. Change temperature. Divide the slime into 2 portions. Place one portion in the refrigerator or in a bowl of cold water for a few minutes. Place the other portion in a bowl of hot water or warm it with your hands. 6. Compare color changes. Take out the slimes from the hot and cold environments. Observe how the color of the slime changes as you expose it to different temperatures. Notice how the slime returns to its original color as it returns to room temperature. Explanation. Thermochromic pigments change color with temperature variations. When the slime is cold, the pigment might appear one color, and as it warms up, it transitions to a different color. This activity demonstrates how temperature affects the properties of matter, in this case, the color of the thermochromic pigment. This activity can be engaging and educational for learners of all ages, illustrating the concept of temperature-induced changes in materials in a playful way. Effect of change of pressure. Changes in pressure can significantly impact the behavior and properties of matter, particularly in gases. Here's how changes in pressure can affect different states of matter. 1. Gas state. Boyle's law. If the temperature remains constant, decreasing the pressure on a gas leads to an increase in its volume, and increasing the pressure leads to a decrease in its volume. This relationship is described by Boyle's law. Charles's law. If the pressure remains constant, increasing the temperature of a gas leads to an increase in its volume, and decreasing the temperature leads to a decrease in its volume. This relationship is described by Charles's law. Combined gas law. The combined gas law combines Boyle's and Charles's laws to describe the relationship between pressure, volume, and temperature for a gas. Ideal gas law. At low pressures and high temperatures, most gases obey the ideal gas law, which relates pressure, volume, temperature, and the number of gas particles. This law helps predict the behavior of gases under different conditions. Le Chatelier's principle. Changes in pressure can also affect the equilibrium position of chemical reactions involving gases. According to Le Chatelier's principle, increasing pressure shifts the equilibrium towards the side with fewer gas molecules. 2. Liquid and solid states. While the effect of pressure on solids and liquids is not as pronounced as in gases, there can be some impact. Changes in pressure can lead to small changes in volume and density in solids and liquids. However, these effects are generally much smaller compared to gases. 3. Changes in phase. Changes in pressure can cause substances to undergo phase changes. For example, decreasing the pressure on a liquid can lower its boiling point, while increasing pressure can raise the boiling point. In the case of sublimation, solid to gas, and deposition, gas to solid, changes in pressure can affect the ease with which these phase transitions occur. Overall, the effects of pressure changes on matter are most noticeable in gases, where pressure and volume are directly related according to gas laws. In liquids and solids, the impact of pressure changes is usually less pronounced and often secondary to other factors like temperature. Understanding the effects of pressure is crucial for predicting how substances will behave under different conditions and is essential in various scientific and industrial contexts. Activity. Marshmallow in a vacuum. Materials needed. A vacuum pump can be borrowed or rented from a science lab or purchased online. Glass jar or bell jar with a rubber stopper and a hole for the vacuum pump. Rubber hose to connect the vacuum pump to the jar. Marshmallow or a similar expandable snack. Stopwatch or timer. Instructions. 1. Set up the vacuum pump. Set up the glass jar or bell jar on a flat surface. Insert the rubber stopper into the jar, ensuring it creates an airtight seal. Attach the rubber hose to the hole in the rubber stopper. Connect the other end of the rubber hose to the vacuum pump. 2. Prepare the marshmallow. Take a marshmallow or a similar snack that expands when heated. Place the marshmallow on a plate or in a small dish. 3. Observe the marshmallow. Turn on the vacuum pump to start removing air from the jar. Watch as the pressure inside the jar decreases and the air pressure around the marshmallow becomes lower. 4. Activate the vacuum pump. After a few minutes, pause the vacuum pump and observe the marshmallow. It should expand due to the lower pressure around it. 5. Release the vacuum. Turn off the vacuum pump and allow air to re-enter the jar. Watch as the marshmallow returns to its original size. 6. Repeat the process. You can repeat the process multiple times to observe how the marshmallow expands and contracts as the pressure changes. Explanation. As the vacuum pump removes air from the jar, the pressure inside the jar decreases. This causes the air pressure around the marshmallow to be lower than the pressure inside the marshmallow. As a result, the marshmallow expands as the trapped air inside it tries to equalize with the lower external pressure. When the vacuum pump is turned off and air re-enters the jar, the marshmallow returns to its original size. This activity demonstrates how changes in pressure can affect the behavior of gases and how substances respond to pressure differences. It's a hands-on way to explore the principles of pressure and its effects on matter. Evaporation. Evaporation is the process by which a liquid substance changes into a vapor or gas state due to an increase in its temperature, even below its boiling point. This transformation occurs at the surface of the liquid as individual molecules gain enough energy to escape the liquid's surface and enter the gas phase. Here's a detailed explanation of evaporation. Mechanism of evaporation. 1. Energy absorption. The particles within a liquid are in constant motion due to their kinetic energy. However, not all particles have the same amount of energy. Some particles possess higher kinetic energy and move faster than others. 2. Energy distribution. The particles at the surface of the liquid have more opportunities to gain energy from the surroundings, such as heat from the air or the environment. As they gain energy, they overcome the attractive forces holding them in the liquid state. 3. Escape from the surface. When particles at the surface of the liquid gain sufficient energy, they break free from the liquid's cohesive forces. They become vapor molecules and enter the gas phase. 4. Cooling effect. As particles with higher kinetic energy leave the liquid, the overall average kinetic energy of the remaining particles decreases. This results in a cooling effect on the remaining liquid, which is why you feel cool when wet on a hot day. 5. Continuous process. Evaporation is a continuous process. Even when a liquid is not boiling, its molecules continue to gain energy and evaporate, though the rate of evaporation may vary depending on factors like temperature, humidity, and the nature of the liquid. Real-life examples of evaporation. Drying clothes. Wet clothes left out in the sun dry due to the heat and air movement, facilitating evaporation. Puddles evaporating. After a rain shower, puddles of water on the ground eventually disappear as the liquid water evaporates into the air. Cooling effect of sweat. The body cools down as sweat evaporates from the skin's surface, removing heat from the body. Evaporation is a fundamental process that plays a crucial role in the water cycle, weather patterns, and various natural and industrial processes. Factors affecting evaporation. Temperature. Higher temperatures provide more energy to the liquid particles, leading to increased evaporation. Surface area. A larger surface area exposes more liquid molecules to the environment, enhancing the rate of evaporation. Humidity. Lower humidity, moisture content in the air, increases the rate of evaporation because it provides a concentration gradient for the vapor to escape into drier air. Air movement. Wind or moving air replaces the humid air near the surface with drier air, speeding up evaporation. Nature of liquid. Liquids with weaker intermolecular forces evaporate more quickly because their particles require less energy to escape the liquid state. Boiling point. If a liquid is below its boiling point, it can still evaporate. However, at the boiling point, evaporation occurs throughout the liquid and is more rapid. Activity. Evaporation exploration. Materials needed. 4 identical shallow containers, example, cups or saucers. Water. Fan or a source of moving air. Humidifier or a source of humidity, optional. Thermometer, optional. Stopwatch or timer. Instructions. 1. Setup. O. Place all 4 containers in the same location. O. Fill each container with the same amount of water. 2. Control group. O. Keep one container as the control group. This container will be exposed to normal room conditions without any additional factors. 3. Temperature variation. O. Place another container in a warm area with higher temperature, near a heater or under direct sunlight. O. Place the third container in a cooler area with lower temperature, near a window or in a shaded spot. 4. Air movement. O. Position the fourth container in front of a fan to provide a constant source of moving air. 5. Observations. O. Record the initial water levels in all containers. O. Use a stopwatch or timer to track the time for each observation. O. Periodically observe and record the changes in water levels in each container. 6. Completion and analysis. O. Continue the observations for a set period, example, 1 hour, or until there are noticeable differences in the water levels. Or compare the rate of evaporation in each container. Which container had the highest evaporation rate? Which had the lowest? 7. Optional. If you have a thermometer and a humidifier, you can create a container with higher humidity by placing it near the humidifier. Compare the evaporation rate of this container with the others. Explanation. This activity demonstrates how different factors affect the rate of evaporation. The container exposed to higher temperature will likely show faster evaporation due to increased kinetic energy of water molecules. The container in cooler conditions will experience slower evaporation. The container with moving air will have enhanced evaporation due to the removal of saturated air near the water's surface. You can also observe the impact of humidity on evaporation by comparing the container with higher humidity to the others. This hands-on activity allows participants to directly observe the effects of temperature, air movement, and humidity on the evaporation rate of water. It provides a tangible way to understand the factors influencing evaporation in our environment. How does evaporation cause cooling? Evaporation causes cooling through a process called evaporative cooling. When a liquid evaporates, the higher energy molecules escape the liquid's surface and enter the gas phase, leaving behind the lower energy molecules. This transition from liquid to gas requires energy, which is taken from the surroundings in the form of heat. As a result, the remaining liquid and its surroundings experience a decrease in temperature, leading to a cooling effect. Here's a more detailed explanation. 1. Energy absorption during evaporation. In a liquid, particles are in constant motion due to their kinetic energy. Some particles possess higher energy and move faster than others. When these high-energy particles are at the liquid surface, they have a chance to overcome the attractive forces holding them in the liquid state. As they break free and transition into the gas phase, they absorb energy from their surroundings to overcome the intermolecular forces. 2. Energy is heat. The energy required for evaporation is taken from the surrounding environment. This energy is often in the form of heat, which is absorbed by the high-energy particles as they escape. As the energy is used to transform the liquid particles into gas particles, there is less energy available to maintain the temperature of the liquid and its surroundings. 3. Cooling effect. The heat absorbed from the surroundings reduces the average kinetic energy of the remaining liquid particles. Lower average kinetic energy means a lower temperature of the liquid. This cooling effect is noticeable as you feel cooler when you are wet and exposed to air or wind. This principle is the basis for natural cooling mechanisms, such as sweating, in living organisms. 4. Examples in everyday life. When you step out of a pool or take a wet cloth and expose it to moving air, you feel cooler due to the evaporative cooling process. In hot climates, people use evaporative coolers, also known as swamp coolers, that rely on water evaporation to cool the air in buildings. 5. Application in nature. Evaporative cooling plays a vital role in regulating body temperature in animals. For example, when humans sweat, the evaporating sweat cools the skin and helps maintain body temperature. Evaporative cooling is a fundamental phenomenon with important applications in various fields, from climate science to engineering, and it provides a tangible example of how energy and temperature are interconnected in the natural world. Why should we wear cotton clothes in summer? Wearing cotton clothes in summer is recommended because cotton is a breathable and absorbent natural fabric. It allows air to circulate, helping to keep the body cool by allowing sweat to evaporate. This helps in regulating body temperature and reducing discomfort in hot weather. Why do we see water droplets on the outer surface of a glass containing ice-cold water? Water droplets form on the outer surface of a glass containing ice-cold water due to condensation. The cold glass surface cools the surrounding air, causing the air's moisture to condense into visible water droplets. Thank you for watching. Please like, share and subscribe.